Alright, today's lesson is tension force. And in a lot of ways, this is not a huge step further than normal force. And as you would have seen in the video, it is essentially a pulling force in a rope or a cable. To make life easier, we make some assumptions, which we'll get into in a minute. So all of these are examples of tension. It can obviously, I think, only pull on objects. Right, so in the picture of the person water skiing, they are being pulled by the force of tension. Right? They are not pushing the boat. Same thing with this person here. He's not pushing up on this wire to push the weights down. We're pulling down, and the force of tension is in the cable in between the two objects that have mass. Now, one of the things that you're going to have to get used to the idea of is that tension is the same throughout the cable. Right? So if this person is pulling with a certain amount of force, this has a certain amount of weight, we're going to see a certain amount of tension that is the same throughout the cable. Now, that is our first assumption that we actually make, that tension is the same throughout the whole rope or cable. In reality, at corners and things like that, actually the tension is greater. We are going to make the assumption it's the same throughout. And then we also assume that the rope or the cable or whatever tension is being exerted through has a negligible mass, as in it has zero mass for our calculations. Just makes life a bit easier for us. All right, so if we can imagine two carts on wheels connected by a massless rope in the middle, how would we determine the tension in the rope? First thing that you should look at actually is just who's going to win the tug of war here. Right? We've got F1 and we have F2. Oops, come on. And I need to change my... There we go. All right, so here's F1, here is F2. Obviously, I think we can see pretty quickly it is going to move towards the right. Right. Now, since the rope is part of the system, the tension in the rope is not included as a force because we only draw external forces on a diagram. It means looking at the system as a whole, we can't actually do anything with it. And so we've got a couple things that we are going to do. All right, the first of these couple things that we're going to do is we need to look at the system as a whole and see, number one, we already figured out who's going to win the tug of war. F2 is going to win the tug of war. What we now need to do is figure out what is the acceleration of the system. And so this is our F net is equal to mass times acceleration. All right, so our F net, I think it should be pretty easy to see. I'll do the calculations in a second, but is going to be 400 newtons to the right. Okay, so we could figure out F net, and this is where you have to put up with me writing with a mouse. So our mass is 15 plus 25, which is going to be 40.0 kilograms. And we've set up our reference system that to the right is positive. 40 kilograms multiplied by our acceleration, which eventually is what we want. And then we also are going to look at this and say, okay, well, F net is actually 700 positive plus negative 300. So 700 newtons to the right, which is positive, plus negative 300, and that's to the left. And it's negative because that's how we set up our frame of reference. And this is equal to our mass of 40 kilograms times A. We're going to divide both sides by 40 kilograms. So we do the addition on the top first, and then we divide by 40 kilograms. Just a reminder, when you are doing this in class, make sure that you are actually doing this and thinking through it, not just mindlessly copying. And if you need to have it paused, just ask and we'll make sure it gets paused for you. So we have 700 plus negative 300 is going to be 400 newtons divided by 40.0 kilograms. I can do this math in my head. It is going to be 10, and it's going to be positive 10.0 meters per second squared, which means it is 10 meters per second squared to the right. All right, so we figured that out. Now, we need to find the tension in the rope. And in order to do this, the rope actually cannot be part of the system since we need to have tension as an external force. So then we must choose one of the masses as the system. So let's choose M1. So the 15 kilogram mass. And either which way, we would set it up kind of this way. Right? If we're looking at F1, right, we're looking at this card here. We know the net force acting on this card is causing it to accelerate at 10 meters per second squared to the right. Net force now on just this card is going to be the Ft plus negative 300 newtons. And we know the mass, we know the acceleration, and so away we go. All right, so let's take a look at this, and you say, okay, well, this time I'll show in a little bit more detail. F net is going to equal F1 plus Ft, right? That's the one way to look at what F net means. All right, at this point, I'd like you to pause for a minute and see what you can do on your own. It's very similar to the one we were just looking at, but now, it's a similar idea to what we were just doing before with the whole system, except now it's smaller mass, but also smaller forces. So pause this, see what you can do with it. We've done similar ones last week with normal force and those accelerating up and down elevators and things like that as well. All right, so first hint, F net is also equal to mass times acceleration. So we have mass times acceleration. We have both of those values equals F1 plus Ft. I'm going to subtract F1 from both sides. And MMA minus F1 is equal to Ft. And our mass is 15. Sig digs is 0.0, so I know I have 3. Acceleration is 10.0 that we figured out from before. I know my diagram doesn't show that it's 10.0, but really it is. Minus F1. Now F1 is 300 to the left, so that's going to be minus negative 300. And that's going to be equal to Ft. And we can punch that into your calculator. So that's 15 times 10 minus negative 300 is going to be 450 newtons of tension. And there we go. Now you could do the same thing. Instead of using cart 1, you could have done the same thing with cart 2 or with F2. And we would end up with the same thing, other than the tension force would obviously here be in the opposite direction. All right. Okay, so I know that you know it's the same but in the opposite direction, but I'd like you to actually pause this here and calculate it as if you pretend you didn't do the other calculation for a moment here. So pause it, go ahead and do that. All right, so you've paused. We set it up exactly the same way. F net equals Ft, oops, needs an equal sign. Come on, there we go. Plus F2. F net is also equal to mass times acceleration, so let's just, here of course the mass is 25, acceleration is still 10, equal to Ft plus F2. I'm going to subtract F2 from both sides to get it over here. So I have MA minus F2. Ft. The mass was 25.0 kilograms. My acceleration is 10 meters per second squared. And again, remembering from the first part, we figured it's actually 10.0, even though I haven't recorded it up at the top with the correct number of sigs. Minus, now this is 700 newtons to the right, and right we've said is positive, so minus 700 newtons, there we go, is equal to Ft. And so I have 250, so 25 times 10 is 250 newtons, minus 700 newtons, equals Ft. Do that on my calculator, and I come up with, indeed, Ft is negative 450 newtons. Remember that with the first part, we calculated it to be positive 450. Here it is in the opposite direction, and so negative 450 is correct. All right, moving on. Pulleys. All right, pulley problems make this a little bit more interesting. So pulleys are used to redirect the tension force. In a pulley problem, the system is no longer rigid, which means that it can change shape. All right, so let's figure out what's going on here. If we draw a force diagram, just looking at this, assuming that M2 is on wheels that will actually start to roll, and M1 is of some weight, M1 is going to accelerate downward, and M2 is going to accelerate to the right. So far, so good. What force is going to cause M1 to accelerate downwards? The answer there, hopefully you can come up with, is gravity. How do we know how much force gravity is exerting on it? Well, Fg equals mg. And so it starts to look a lot like the last question, the difference here being that the force exerted on M1 is because of gravity rather than somebody pulling on it. Right? So remembering, of course, tension is an internal force. The vertical forces on M2, we don't need to worry about it. Yes, gravity pulls down on M2. Yes, the normal force is pushing back up, preventing it from going through this line on the countertop, going through the countertop. But we ignore those forces because they are balanced. And now we're using these ones, which I know some of you don't love. But these ones are helping us to figure out what's going on. So force of gravity on 1 is equal to the mass of 1 times the acceleration due to gravity. Now, the easiest way to do this is we're going to rotate this so that it becomes a 1D, one-dimensional rigid equivalent system, right? So we can imagine, instead of it accelerating downwards here, it's just moving to the right, that everything moves to the right with an applied external force of Fg1, which is equal to m1g. And at this point here, we're saying, okay, the acceleration of the whole system is equal to Fnet over m. Now, at this point, I don't think I did this in the next slide. Oh, here we are. Yes, I did. Help you out with this. The acceleration is going to be this force over the whole mass of the system, divided by m1 plus m2. And then this is important too. It's a smart idea to just say, well, the direction of the acceleration, that is going to be our positive direction, and that is okay to put that as your reference. And this is especially good when you get to pulleys where one mass is going up and the other mass is going down. We'll just say the acceleration direction is positive. So our force is just m1g. So this is our applied force, which is the net force, the only force acting on this system, because we haven't said anything about friction or resistance. And it's acting on the whole system, which is at mass 1 plus mass 2. All right. Force diagram on this, given that m1 is greater than m2. So one of the things we got to look at here, I don't think, yeah, I did start to draw it here. We can ignore tension because it is an internal force. Now, obviously, there is tension in this rope in the middle, but if we're looking at the whole system, we don't draw internal forces. So we're also not drawing whatever tension forces are holding M1 as one piece and M2 as a second separate piece. Right, so we have two forces. Could you predict the equation for acceleration? I'm sure if you looked ahead, you would see it here. But we're going to rotate it so it becomes a 1D equivalent system. Newton's second law gives us the acceleration equals F net divided by m. Now, this mass is the mass of the entire system. F net, this is going to be Fg1 plus negative Fg2, or plus Fg2, but Fg2 is negative. Can't remember. And so it works out once we start putting numbers in is m1g plus negative, or just minus m2g, all divided by the total mass of the system. So if you're not liking the 2's, I'm sorry, but you're going to have to get used to using subscripts, because otherwise we have a whole bunch of m's that we really are not sure what we're doing anything with. Right. So as we move on, let's actually go through a question here. So we want to determine the magnitude of the acceleration and the tension in the string. These are given, mass is given in grams. So first of all, which way is it going to move? I know it's not asking direction, but this is actually going to help us. It's going to move, well, M1 is going to move down, M2 is going to move up. That's going to be the direction of our acceleration, right? We should change these into kilograms. So as we look at our system here, kind of defining the forces where M1 is greater than M2. M1G is our applied force pulling down. M2G is our resistive force. And we're going to rotate it so that it's as if it is all in one straight line. And then we set it up this way, where it's going to accelerate to the right. So we're going to say right is positive, left is negative. And we want acceleration. So acceleration is equal to F net over total mass. Now our net force is going to be F1G, or FG1 I should say, plus, this was FG2. I've done some work for you on the screen just to show you what we're already, it's kind of, a look ahead, divided by M1 plus G1, right, total mass. Sorry, M1 plus G1, M1 plus M2. So my acceleration, let's start to put some numbers in. FG1 is going to be M1G. M1 was our 0.8 kilogram mass. At this point, pause the video. See if you can figure out for yourself and get the next steps done. Because in this case, the acceleration of quote-unquote gravity, we're assuming it's to the right. This 9.81 going with M1 is actually positive. Again, because that's the direction of the acceleration, so it's got to be positive. And the reason that the other side, we've got a negative there, is to remind us that this is going in the opposite direction. And so this was my 0.5 kilogram mass. And here our acceleration due to gravity is going to be negative 9.81. All divided by M1 plus M2, sorry, which I should also start writing in, which are going to be 0.800 kilograms plus 0.500 kilograms. If I'm putting this in my calculator, I got to make sure I have brackets around everything at the top as well as everything at the bottom if I'm doing it kind of all in one step on my calculator at this point. Otherwise, I can do the top part first, divide by, and then put the bottom stuff in brackets. And both ways will work, but just make sure that you do put brackets if you're trying to do it all in one big step. And we end up with an acceleration of 2.26 and stuff. We're going to keep that unrounded value. So the calculator spits out, I don't know, 2.2638 and so on. Store that in my calculator so I can use it later on because I'm going to need it. All right. So now that we know the acceleration, how do we determine the tension? And we are going to determine the tension similar to what we did with that first one with the rope in between the two pulleys. We have a force on either end, and away we go. We also have tension in the middle acting on each box separately. So let's use M2G on M2. And away we go. F net is equal to Ft. We're still using the same reference system, by the way, that right is positive, left is negative. So Ft plus Fg2. Ooh. And Fnet still is equal to mass times acceleration, so Ft. And we're going to subtract Fg2 from both sides, so I'm going to actually rewrite this already. Okay, so you can see I'm going to do two things at once here. I'm going to subtract Fg2 from both sides, and also substitute in at mass times acceleration for Fnet. And that's going to give me my tension force. So the mass of object 2 is 500 grams, or 0.500 kilograms. My acceleration, I just calculated it momentarily ago, is going to be 2.2638. That's that big number that I'm hopefully storing in my calculator. And minus m2g. So this is, again, our acceleration for gravity in this case is in the left-hand direction, or it's resisting the motion of the thing. So it's going to be 0.5. And this will be a negative number. And now it's a matter of just punching some numbers in my calculator. And my force of tension is going to be 6.036, which works out to 6.04 newtons, 2 sig digs. All right, and again, if you had chosen, instead of this one here, to do this side of things, what you would calculate is that Ft would be the same magnitude, so 6.04 newtons, but it would be in the opposite direction. What this really means is if this rope in between the two objects cannot withstand 6.04 newtons of force, it will break, and then our pulley will fail. Other than that, I will have an assignment up on Google Classroom and in the subplans. Thank you so much.